Hello, everyone. Welcome to Griffith Observatory's Summer Solstice stream. Today, we are celebrating the summer solstice in the Northern Hemisphere. It is June 21st, 2023, and we are coming to you live from Griffith Observatory in the city of Los Angeles. As always, this program is brought to you by the Department of Recreation and Parks and the City of Los Angeles, who own and operate Griffith Observatory. But as always, we like to thank our exclusive nonprofit partner, Griffith Observatory Foundation, and all the people that support the foundation and help us make programs like this possible. With me today, as is usual for our solstice and equinox performances and programs, is Patrick So.
Hello.
And of course, we also have Dr. Edwin C. Krupp with us, our director of Griffith Observatory, to provide our main topic today, inhabiting the Meridian, and also the performance at the Meridian Arc. Hello, Dr. Krupp, are you here?
I am completely aligned with the summer solstice.
Fantastic. It is a lot of fun, and you will get to see how Griffith Observatory performs as an instrument. We actually have instruments that observe events and moments in time like the summer solstice, and we will show you how all that happens. And like I said, today is the day that we celebrate the moment of the summer solstice, as you can see here. Now, you might wonder, why are we talking about it at noon? Well, we celebrate something called local solar noon. And it doesn't happen exactly at 12 noon. Yes, our broadcast started at 12 noon. We were very prompt and timely on that. But the event that we'll be celebrating today at this broadcast is something known as high noon or local solar noon. It's the point in the day where the sun is highest in the sky. In a lot of old movies like this Gary Cooper movie, the gunfighters would agree to meet at high noon. It was a thing they could watch as the sun got higher and higher in the sky. They knew that moment in time where it was highest and began its descent back towards the west. That moment is local solar noon, and we're going to celebrate that today. Now, if you want to go look at it, I don't recommend you look up in the sky. It's rather hard to do, but if you're going to look at the sun, make sure you have the proper protection. We always like to point that out. If you have the urge to go look up at the sun, make sure you get a pair of proper eclipse glasses. Now, today, like I said, we are celebrating that moment when the sun is going to go higher and higher in the sky, and then it will peak. And that's going to happen, like I said, not at noon, but much later today. And as you stay tuned for the broadcast, you can see exactly when that happens. I don't want to spoil the fun. But that is the local solar noon. You might want to know, why does it not happen exactly at noon? Well, part of the reason is time zones. Our entire Pacific time zone has the same time. And obviously, the sun can't be directly overhead for everybody in that time zone at the same time. So within a single time zone, local solar noon will happen at different times. In addition, we're, of course, in daylight savings time. So that's caused another shift of an hour. And then on top of it, the Earth's orbit is not exactly circular. So the solar time drifts a little bit with respect to clock time. So those actually don't, they agree a couple of times a year, but they will drift with respect to one another because the Earth's orbital speed around the sun changes. Now, as you can see here in this image we're looking at, there are many time zones across the Earth, and they all are not equal in size. They're not all straight up and down. The lines change shape. Those are done for political reasons and for social reasons and for human reasons. So as people, we make adjustments to serve our needs, whereas astronomy is a little different. Of course, it's going to follow the celestial mechanics and the laws of physics in the universe. So, Patrick, today is what we like to call the Northern Hemisphere summer, the first day of summer. Yet in the Southern Hemisphere, it's the first day of autumn. What's going on with that? Can you help explain why those two are different?
Yeah, we'll just go to the next slide. And we got an early start for summer solstice because it occurred at 7:58 a.m. Pacific Daylight Time today. And as you can see in this diagram, the northern hemisphere and the north polar axis of the Earth is tilted towards the sun. And this means that the sun is rises far in the northeast and climbs to its highest point in the sky from Los Angeles. It's about 79 degrees at local noon, which occurs at 12:55 p.m. Pacific Daylight Time today. And then it sets far in the northwest. So being that the sun is much higher in the sky, it means that we have longer days and shorter nights. In fact, the longest day today and the shortest night tonight. And conversely, in the southern hemisphere, you can see that the South Pole axis is tilted away from the sun. And conversely, it's the first day of winter in the southern hemisphere, which means that the sun rises uh, well, in the same direction, but it doesn't climb as high in the sky. So it's like when we experience winter here, we see the sun is low during noontime. So it doesn't stay that much long in the sky, and therefore the day is short and the nights are long, and it's a lot colder too.
Yeah, exactly. Those are all reasons we experience our seasons, and it's because of that tilt of the Earth's axis. Now, a lot of folks think the tilt, a lot of folks think it wobbles around like this over the course of a single year. It doesn't do that. It doesn't wobble like a top that quickly. That motion, the Earth does wobble like a top. It takes almost 26,000 years. So that's not the cause of the seasons. In fact, our North Pole is pointed very close to the star Polaris, and it maintains that position year to year with a very small drift, too small for us to notice over the course from one year to year with our human eyes. But so how does that cause the seasons? Let's take a look here. You'll notice when the Earth's axis is neither pointed towards the sun nor away from it, that line of shadow is kind of straight up and down on the Earth. It goes from the North Pole to the South Pole, and the North and South are getting equal amounts of daylight, equal amounts of night. Those are the equinoxes. And like Patrick described, when the North Pole is tilted towards the sun, in other words, when Polaris is off in the same direction as the sun, roughly, we get a lot of sunlight up here in the north and the south gets less. And then, of course, on the first day of winter, that's for us up north, that's the first day of summer for the southern hemisphere. We're exactly opposite from one another. Now, a lot of folks get confused and think that the seasons are caused by the Earth being closer or further from the sun. It's actually not the case. We are closest to the sun on January 3rd. So that's in the middle of Northern Hemisphere winter, and we're about 147 million kilometers away. And on July 3rd, so just a handful of days in the future, we're 152 million kilometers away. So a significant distance further away from the sun, yet we're entering summer. So it has an effect, but that tilt has a much bigger effect. So the tilt is the driving force for these seasons. Now, like I mentioned, we are going to observe this first day of summer in the Northern Hemisphere, the solstice, by observing local solar noon with our Meridian arc, which is in the Gottlieb Transit Corridor here at Griffith Observatory. And our very own director, Dr. Edwin Krepp, is going to tell us all about inhabiting the Meridian and about where else these can be found and how special our instrument is. So, Dr. Krepp, back to you.
Well, thank you, David and Patrick, and thank you everyone for tuning in today to Griffith Observatory Television and observing with us the summer solstice, and in particular, in a short time from now, local noon in Griffith Observatory's Gottlieb Transit Corridor. Looking for, I'm afraid, the PowerPoint here. If you can bring it in for me, thank you. Super. The exact moment, as you already heard, of summer solstice occurred earlier today at 7:58 a.m. Pacific Daylight Time. Local noon, as you also heard, occurs today at Griffith Observatory at 12:55 p.m. That's Pacific Daylight Time. And as a prelude to local noon, we'll spend a little bit of time with the meridian, which is inextricably linked with local noon. The meridian, of course, is a fundamental reference in our system of directions. It's just the line that runs on the ground from true north to true south, or back in the other way. And in this diagram, you simply see a dotted line headed out to the north to indicate the meridian line on the ground. And of course, wherever you go, there you are on some local meridian. In fact, there's a local meridian right there inlaid in the ground with metal. Many monumental activities were intentionally aligned with the meridian. Actually, our maps are oriented by the meridian. That's a map of Washington, D.C., which is cardinally oriented. That is, oriented to the cardinal directions. District of Columbia's, the corners of that territory, where it has corners, are in the north, south, east, and west directions. Again, our grid plans of many major cities are built to it. That's the grid plan of Chicago, which is very accurately laid out on a north, south, east, west, or meridian plan. And in fact, even the design of Griffith Observatory adheres to it. The main axis of Griffith Observatory and its grounds is a north-south line going to the top and the bottom of this view here. Well, the meridian originates in the basic behavior of the sky and is a fundamental astronomical reference. It's probably most familiar to people as the prime meridian, and that, of course, is the meridian at Greenwich in England. The Greenwich meridian is particularly famous because it serves as the adopted 0 point for longitude on Earth. It's a primary attraction at the old Royal Observatory at Greenwich in England. People, in fact, stand on the meridian. People sit on the meridian. People, of course, observe on the meridian. So the meridian is a north-south line, and we identify those directions, north and south, through the most fundamental motion of the sky, its daily rotation. And thanks to the spin of the Earth on its axis, the entire sky seems to point around a single unmoving spot in the sky, that is the North Celestial Pole. And Polaris, the pole star, as you've heard, is fortuitously close to that position. And so it's easy to find in our night sky in the northern hemisphere because there happens to be a star near that geometric point in the sky now. Now, the direction on the ground directly below the North Celestial Pole is north. That, in fact, is how the direction north originates. That's from where it comes. We wouldn't even be talking about north if the world didn't turn like this. But as the world turns, that great terrestrial soap opera allows the sky to deliver the directions. And as the sky rotates around the North Celestial Pole, the objects in the sky, the sun, the moon, the planets, the stars, all cross or transit the meridian, and at transit, any celestial object is at the summit or top of its daily arc across the sky. And as you've heard, the top of the daily arc of the sun, visible in this view, imagined view of looking outside the heavens from outside and looking in toward the earth as if the earth were at the center of the universe. And that happens to be the winter solstice, the southernmost sun crossing from the southeast and rising up to an arc that goes to the top of this globe. That's the local meridian there in the picture, and then it goes down into the southwest. But each celestial object crosses that arc that rises from the horizon and up to the top of the sky, and then back down again. Well, the word meridian is rooted in words that mean midday or noon. And when the sun transits the meridian, it is, as you've heard, local noon. When the sun is east of the meridian, it is ante-meridium, or AM, before midday. When the sun is west of the meridian, the Latin gives us post-meridium, or PM, which is after midday. And just for the record, noon is neither AM nor PM. So whenever you see something written as 12 AM or 12 PM, that's just wrong. Same is true for midnight. So the meridian is a time and a place and a direction. The meridian is also that celestial arc that vaults the sky from the north point on the horizon through the zenith point directly overhead to the south point on the horizon in the opposite direction. And from the surface of the earth, the distinction between north and south is profound. The stars travel in circles around the North Celestial Pole because, of course, the earth is turning. And in the diagram, it's easy to see how any star on any one of those positions seems to move around that central spot of all of that circular motion. If you look to the south, the stars appear to be following longer and flatter trajectories across the south point. They really are still traveling in circles, but their migration looks strikingly different, again, just due to the geometry of our position on the surface of the Earth. Well, our ancestors were aware of these directional distinctions, and our ongoing use of them is really just a perpetuation of old habits. Evidence of these habits shows up in many ancient and prehistoric sites. For example, a natural rock shelter enriched with pictographs at Alder Creek in Chumash Territory in Ventura County in Southern California seems to have been chosen for this symbolic enhancement because by chance it opens due north. In this view, you're inside that shelter and you're just looking out to the north. But when the sky grows dark and the stars come out, it's evident that the North Celestial Pole and Polaris, the brightest star in that view, are right in the window of your scene as you're sitting inside the shelter. And that slant of the shelter is, of course, accidental, but it probably was sought out. It was probably found and used by the Chumash, who painted on it the various figures of rock art on the ceiling. And all of these figures appear, in fact, to be following a natural crack in that ceiling that slopes upward toward the North Pole of the sky, as if, in fact, they are headed in that direction. And these spirit creatures painted on the ceiling then follow that crack upward and out to the North Pole of the sky, a destination of supernatural shamanic power in Chumash Indian tradition. Now, the same principle is deliberately expressed in monumental architecture in Chaco Canyon in northwest New Mexico. Pueblo Bonito here, a large multi-story apartment complex, is oriented with the Meridian, and you're almost looking along that north-south line from the cliff above it. And that north-south line then commemorates its orientation in a north-south wall that bisects the two halves of it. Here's the plan of Pueblo Bonito. You can see the two halves with a wall that splits that sort of D-shaped structure in two. And in fact, you can look right along the wall and see the two halves of the Pueblo Bonito structure there. There's more to it than just that singular building, of course. The Great North Road, which is a construction by these ancestral Pueblo people, symbolically departed Chaco Canyon's north rim and passed shrines and landmarks on a straight line to cardinal astronomical north, tens of miles in that direction. Beijing, in the People's Republic of China, is the only world capital that is still adhering to a sacred cosmological plan. During the Ming Dynasty in China, it was laid out on a meridian, a north-south line that's evident in the plan of the imperial palace here, and it's been preserved by the current regime. It's also apparent in the ritual walkway of the imperial palace. And so, in fact, you're marching here toward the Hall of Supreme Harmony in the very center of the imperial palace, and that walkway does get defined by the meridian line, the north-south line. That line was focused on the emperor, who held court in the Hall of Supreme Harmony, and he was the sky's agent on Earth and the terrestrial counterpart to the North Celestial Pole. Just as the North Celestial Pole anchored the sky, the emperor was perceived as anchoring the Earth, anchoring the empire of China in place by his rule. And so just as all the stars circumambulated around the North Pole of the sky, the visible face of the high god Shangdi, the court circulated around the emperor. Now, Egypt's Great Pyramid at Giza and the rest of Egypt's pyramids are also cardinally oriented. By incorporating cosmic order into monumental architecture, the Egyptians miniaturized the cosmos in a terrestrial setting. It was like bringing the universe down to Earth and thereby transforming it into sacred space. That is, in fact, what we really mean by sacred space. And the plan of Giza shown here just indicates that all of the monuments built there, it's really a giant cemetery from Egypt's Old Kingdom, are all aligned north-south and east-west. Now, the observatory of Guozhou Jing, a 13th century Chinese astronomer at Gaocheng in north central China, operates like a sundial to establish and refine the calendar with shadows that are cast along a low meridian wall. A rod that is positioned in a doorway up at the top of this small pyramid allows sunlight to pass through it and cast the shadow of that rod down to the left in the view. High sun casts a very short shadow, low sun in winter, a very long shadow. And they all fall upon this low wall that extends then out to the north and on which the length of the shadow could be measured to establish with high accuracy and high precision the length of the year and the calendar. These principles were applied even more elaborately in the 14th century by the Islamic astronomer and ruler Ulugh Beg at Samarkand in what is now Uzbekistan in Central Asia. This is a cross-section of Ulugh Beg's observatory at Samarkand, and you can see that it includes a large arc that sweeps from the upper left down to the lower right. And apertures in the upper right corner permitted light from celestial objects to shine down onto that arc. And by the position measured on that arc, the positions of those objects could be determined. Well, the fact is, Ulugh Beg put that arc on the meridian. You can still see a portion of it today in Samarkand. And he observed with it transits of the sun like this, where a beam of light would fall upon the inscribed arc and so allow very accurate measurements and of the sun and other objects on behalf of timekeeping, calendrics, and star mapping. While Europe developed its own calendrical revelations in architecture with giant meridian scales that were installed in churches. And the diagram here shows a high wall of a church imagined with a hole up near the top of that wall that's on the left of the picture. Well, the sun can shine through that hole, and depending on the height of the sun over the course of the year, once again, it may either send a beam to create a short spot of light, a short distance from the wall, or one that goes at a very long distance from the wall. The contrast again between winter with the long position and summer with the short position. These structures that were installed in churches were at first intended to monitor the progress of the year calendrically, just as I've described. But these meridianas, as they're called, were eventually inscribed on church floors by astronomers for precise measurement of the sun's daily noon elevation. The one we're seeing here illustrates a meridiana that was designed in 1575 by Ignazio Dante in San Petronio, which is a 14th century Gothic basilica in Bologna, Italy. Now, that aperture on the vertical wall rising beyond the south end of the calibrated meridian line then permits that pinhole image of the sun to cross the meridian each day at local noon. And the point where the sunlight intercepts that line on the ground then, of course, depends on the sun's noon elevation. And because that angle depends on the date, the meridiana directly operates as a calendar. Well, Dante's San Petronio Meridiana was never completed, but it was replaced in 1655 by an even grander Meridiana designed by the astronomer Gian Domenico Cassini, and that's still in place in Bologna. Cassini's 220-foot long meridian, still embedded in the cathedral stone floor, still works. And so now we're looking away from the wall that has the hole that permits the sun to shine through. And so we're looking to the south in the cathedral. And here, in fact, is sunlight crossing the meridian at local noon on November 18th, 2004. This is Meridiana in the old upper part of the town of Bergamo in northern Italy, and it's operating like clockwork on October 14th, 2009. So, of course, formal observations of the sun's meridian transits persisted in national observatories like the Paris Observatory, the cornerstone of which was laid on the summer solstice in 1667 during the reign of Louis XIV, the Sun King. And France adopted the axis of the Paris Observatory as its preferred primary meridian. Well, Jean-Dominique Cassini was invited to Paris to assist the development of the new Paris Observatory, and he became the first director. And extending the inquiry that he had undertaken at San Petronio, he constructed a large meridiana in the Great Hall on the second floor of the Paris Observatory, seen there. It's 96 feet, 10 inches long. He wanted the building to perform as an instrument, and he designed his meridiana to coincide with the meridian of France, which is marked right there on the observatory grounds outside the observatory building. And so with this meridiana, he planned to obtain a more precise determination of the apparent annual motion of the sun. So these instruments were actually used for fundamental astronomical research. Despite the French preference for a French prime meridian, the local Greenwich meridian, occupied by George Airy's transit circle, was officially adopted as the prime meridian of the world in October 1884 at the International Meridian Conference held in Washington, D.C. Airy was England's astronomer royal, and his transit circle, still in place there today at Greenwich Observatory, was being used in the service of British cartography. The old Royal Observatory had been established in 1675 by King Charles II, who wanted it dedicated to finding out the longitude of places for perfecting navigation and astronomy. But long before England and France drew a line in the land for 0 degrees longitude, astronomy in medieval India staked a meridian claim, a prime meridian claim through Ujjain, which is a city about 400 miles south of New Delhi. It's in central India, and it was believed to occupy the Tropic of Cancer. That is the latitude at which the summer solstice sun appears to pass straight overhead at local noon. So it was, in fact, given status for that reason at the time, and the observatory was built there by Sawai Jai Singh II, the Rajput ruler of Jaipur. Sawai Jai Singh II built Ujjain in 1730, but he built 4 more monumental observatories, and his most elaborate observatory is in Jaipur. There, the great Samrat Yantra, which is what you see here, makes sculpture and architecture out of an instrument. It includes a particularly interesting component, the Sastamsha Yantra, which is there's the door for it. It's a cardinally oriented room, relatively small, that houses a pair of inscribed quadrants. You can see the arc of one of those quadrants aligned with the wall of the room in that view. And that room also permits light from the transiting sun at local noon to enter the darkened chamber through a pair of small holes that penetrate the southern wall. We're looking there up at the southern wall, and in fact, sunlight is already coming through one of those apertures and sending a spot of light on the wall that is adjacent to the one of those 2 arcs. Well, those 2 holes project pinhole images of the sun onto the 2 quadrants that are allowed then to permit direct observation of the astronomical declination. These arcs are inscribed meticulously so that the angle can be measured, and there's the other one. And those measurements then are linked to the calendar and the progress of the year. So there are all kinds of meridians around the world, but anybody who collects meridian markers now must navigate a course to Los Angeles. Everybody knows about the Greenwich Meridian, but this is the Griffith Meridian. Griffith Observatory is cardinally oriented. It faces to the north, and its telescopes are aligned with the North Celestial Pole to facilitate continuous tracking of celestial objects. And although Griffith Observatory was conceived and constructed to conform to the needs of public astronomy, its Greek Revival Beaux-Arts modern architecture reflects, with its orientation, the traditional vision of cosmic order. Telescopes operate on this principle. The telescope is rotated around the polar axis. That's that axis that's perpendicular to the telescope tube in this particular view. And that compensates for, that motion compensates for the turning Earth. The sundial's also aligned with the meridian. That allows it to work and permits its shadows to convey the time systematically. And the mirrors of Griffith Observatory's triple beam celestat or solar telescope also are on the meridian and track the sun as it moves from one side of the meridian to the other through the course of the day. Well, the Griffith Meridian is actually part of a singular and monumental public instrument, the Gottlieb Transit Corridor. There's really nothing else like it anywhere else in the world. This instrument is integrated into the observatory's new architecture on the west side, where parallel glass walls, 150 feet long, 20 feet high, preserve below grade the observatory's signature vista of the western horizon. And this instrument also demonstrates how the sky works through meridian transits of the sun, moon, and stars over the walled corridor. The corridor, 10 feet wide, is bisected by the bronze meridian line that is set into the concrete floor, and it extends the full length of the walls. And the walls themselves frame the celestial meridian, the arc, or that ribbon of sky that connects the south point through the zenith down to the north point opposite the south. And they turn this astronomical abstraction into an immediate visual experience. Well, the architecture then reveals the astronomy. Now, at the north end of the instrument, the meridian line climbs a stairway that is constructed to ascend at the angle of the North Celestial Pole. That's designed into the angle of the stairway. So at night, visitors can just go up to the banister and sight the North Star along the stairway's central banister. The fundamental character of Griffith Observatory is actually indicated right on the front of the building, where the bronze letters declare Griffith Observatory. It's an observatory, and it puts visitors' eyeball to the universe, and that's what its instruments are all about. Griffith Observatory, then a public observatory, and the building is filled with instruments. All of them deliver real data and real experiences in real time and transform visitors into observers of nature and the sky through instruments. So we are mobilized then by the concept of the building as instrument. The Gottlieb Transit Corridor is just another dimension of that immersive encounter with the sky. And there is more to it than the long glass corridor, the North Stairway, and the bronze meridian line. At the south end, a tall, night black monolith supports a stainless steel foil, a piece of stainless that is bent at an angle, and on the ground just north of the pillar and the foil is in fact the large meridian arc, bronze and stainless as well. And above it, on the inside face of the glass wall on the west, is mounted a huge and heavy ecliptic chart. So there is the monolith and the foil, and the chart is on the wall. Well, the foil attached to the monolith is equipped with a complicated and technically advanced device, a hole. And as an object, say the sun, transits the corridor, its light passes through the hole and produces a spot of light that falls upon the meridian arc, as you see here. Where that light falls depends on the angle the object makes with the horizon, and an object reaches, as you've heard now many times, its highest elevation when it transits. Well, the monolith and the foil permit light from the transiting sun to strike the meridian arc where the sun's image, about 3 inches in diameter, announces the date on a scale that's inscribed with the months and with the days and with the corresponding ecliptic or zodiac constellation figures. Special emblems also spotlight the solstices. There's a special mark for summer solstice on the arc, the equinoxes, and the major standstills of the moon. That's a much longer cycle for the moon, takes 18.61 years, but we're coming up to the major standstill of the moon in 2024. And of course, that'll be observed from Griffith Observatory as well. So people walk inside the transit corridor, they watch all of this, and they also watch it from the terrace above. Now, actually, Tycho Brahe already did something like this. In 1582, he fabricated and installed a large bronze engraved meridian arc for transit observations in Uraniborg, the castle observatory he built on the island of Ven, just off Denmark. We, however, have linked the meridian arc, where the sun makes its daily noon transit, with that big star chart on the wall. You can see it up to the left of the meridian arc in this view, or a closer view of it there. So as the sun's light reaches the meridian arc and gradually moves across it, it heads toward the center line of the meridian arc. And it eventually, in just a few moments, reaches that line of dots at the center. And those are sensors built into the meridian arc. And when that spot of light actually crosses those sensors, they transmit a signal up to the giant ecliptic arc, and that signal prompts the illumination of lights that mark the current position of the sun along the ecliptic with respect to the background stars. Now, those background stars, where the sun happens to be at that moment, are up in the daytime as well as the sun. And so you can't see them because, of course, the sun is up. But the ecliptic chart also lights up the stars of the zodiac constellation that the sun happens to be occupying. And at the time this photograph was taken, the sun was in the constellation of Taurus the Bull. And so not only do we see the 5 dots marking the position of the sun on the ecliptic, but we also see the stars of Taurus the Bull lit up as well. So the meridian is a place and a time and a direction. And when visitors arrive at this junction of earth and sky, they occupy a place where space begins, a cosmic modem that downloads the sky. They connect what happens in the sky with place and time and direction here on earth in a dramatic, precise, and content-rich revelation in light. The meridian is not then just an instrument or a concept. It's a stage, and the universe performs on it daily. And we're going out to that stage in just a few moments for local noon at 12:55 p.m. Pacific Daylight Time on the Griffith Meridian.
Thank you for that, Dr. Krupp. Fascinating as always. And it's nice to know Griffith Observatory's place with respect to the history of instruments like this and how we are carrying on a tradition of observing the sun and local solar noon. And indeed, today is a special day to observe local solar noon. The spot of sunlight crosses our meridian arc in the Gottlieb Transit Corridor at the lowest possible position. It crosses right at the very, very bottom of it because the sun is so incredibly high in the sky. So we will get to see that, which is very, very interesting. As Dr. Krupp makes his way down to the Gottlieb Transit Corridor, we are we're lucky today to have two events that we celebrate, not just local solar noon, but we also have lines marked out in the sunset terrace, marking the direction that the sun will set. And today, the sun sets as far to the north as it sets the entire year. So if you're in the LA area, you can come on up to Griffith Observatory and actually watch the sun set, and it will go down along one of the lines, as you can see here, which this is an example of it setting quite far to the north as it does on the summer solstice. That broadcast begins tonight. Patrick, what time is that broadcast again begin?
It's 7:45.
7:45, exactly. I knew it was a little bit of an odd time. And the sunset itself happens just after 8 o'clock. Usually I like to talk about the significance of the day, and then I let folks enjoy watching the sunset itself, and we'll put on some music. And then after that, provided that it's clear and provided that all goes well, we have a beautiful view of the moon and Venus in our western sky that we'll also be able to bring you some gorgeous shots of live from Griffith Observatory tonight. Last night, the shot was just very, very pretty. And from my knowledge of astronomy, I know the moon is going to be even closer to Venus tonight, providing just a really beautiful view. So I encourage all of you to go outside tonight and take a look at that view on today's solstice. We have a nice crew who have joined us on the YouTube channel, so I just want to say hello to everybody in the chat that's chatting happily with one another. We always appreciate you joining us for these events. And I'm going to take just a moment once again to explain that today's presentation is brought to you by the Department of Recreation and Parks and the City of Los Angeles that own and operate Griffith Observatory. And as always, we like to thank our nonprofit partner, Griffith Observatory Foundation, and all the individuals that make donations, all the members, and also all the grant funders that help us with our programs. We appreciate all of you. Thank you very much. So Patrick, we started doing these broadcasts. It was shortly after the pandemic when we had to close, and we've come to notice that folks gather together to mark these events, mark these moments in time. And in some ways, it's a celebration of the celestial mechanics, the fact we can predict these, that we understand how it all works, and the physics. So, and yet there's a deep history of folks marking these moments in time when they didn't understand how the celestial mechanics went. And I think that draws a lot of people into wanting to know more. And here at Griffith Observatory, we can tie the two together. We tie together the cultural aspect of it, the fact that people have been making observations like these across time. We make them today, and then we bring you the science as well. And that's what can be special about it, is you can feel connected to people over the ages that have made observations just like this, and yet you can understand that this is due to the Earth's motion around the sun, and it's due to the tilt of the Earth's axis. And all of this is very, very understandable and predictable. So you can both enjoy the wonder of it, the awe of the spectacle, and also celebrate the science. And that is something we do here at Griffith Observatory. Question, will we be broadcasting the solar eclipse on October 14th? Potentially. We are not along the center line. We are instead going to have an eclipse it's over 70% eclipsed here in Los Angeles, if my memory serves. So it's a pretty eclipsed sun we will see, but not being along the center line, we won't see the annularity. It's an annular eclipse where the moon's a little too far away to completely cover the sun. We probably will bring you something, so stay tuned for that announcement. Go ahead and follow our YouTube channel and sign up for the notifications if you haven't yet, and we'll be sure to keep you informed of all our plans. Other events that we do run, I want to let you know about All Space Considered. That's a live space news show we do, and it usually occurs on the third Thursday of every month. We moved it recently, and if we have to, sometimes it might drift to the fourth Thursday or the second Thursday if there's an event that conflicts. But if you like space and you like this sort of thing, be sure to join us on those programs. We have a lot of great guests and a lot of fun talking about what's up there in the sky, both bringing you what things you can see. Patrick does our sky report, but also we talk about things professional astronomers have measured and discoveries that have been made. So we have a lot of fun with our All Space Considered show. We have been bringing you terrific. We have been bringing, I just got a report that Dr. Krupp has made his way to the Gottlieb Transit Corridor, and we're about ready to start with him and observe the moment of local solar noon. But I just want to mention that we do these sorts of broadcasts for all of our equinoxes, most of the major sky events that occur here in Los Angeles, and like I said, All Space Considered and other events. And if you like things like this, consider signing up for the Griffith Observatory Foundation. That's, like I said, our nonprofit partner, and the members there have a lot of fun. They have a lot of opportunities to do additional astronomy things. And even if you're not a member, you can sign up to get their newsletter and see what's going on here at Griffith Observatory. Well, now Dr. Krupp is ready, and we are going to take you live to the Gottlieb Transit Corridor at Griffith Observatory. Oh, and I'm hearing them. All right, well, I'm hearing the live sound. No camera yet.
This is Dr. Ed Krupp, Director of Griffith Observatory, broadcasting live from the Griffith Observatory Gottlieb Transit Corridor on the summer solstice, the longest day of the year, that is the longest period of daylight hours in the Northern Hemisphere, and of course the time of shortest nights. We are using events like the solstice to mark out our seasons. And this is not new with us. This goes back to our ancient ancestors, probably, in fact, tens of thousands of years. But we're still continuing the tradition at Griffith Observatory. It's built into our calendar, and in fact, it's built into Griffith Observatory. The Gottlieb Transit Corridor is a monumental instrument that allows us to see the sky actually working in real time. And we're here for local noon in the Gottlieb Transit Corridor on the summer solstice to see how the sun indicates the date and the time of its highest passage across our sky. We are, in fact, on the local meridian. Everybody that's around me here, of course, they know the Greenwich Meridian, as we mentioned earlier on the broadcast. This is not the Greenwich Meridian. This is the Griffith Meridian, which is a very impressive, I mean, you don't see this kind of stuff at Greenwich, I'll tell you. But the Griffith Meridian is, in fact, our opportunity to watch the sky as it's actually performing for us seasonally and, in fact, even every day. And the event that we're about to observe is local noon. And as mentioned in the broadcast earlier, local noon doesn't really occur at noon. I mean, when the big hand and the little hand are on the 12. Of course, that makes no sense to anybody anymore with clocks like that. But nonetheless, we're well past so-called 12 noon by our clock time. And if we're going to have any kind of understanding at all of what's going on here, the first thing we have to do is make sure we understand why local noon isn't taking place at noon. And there are three main reasons. And the first one is given by letters. PDT. That's Pacific Daylight Time. So even if everything else were working out all right, we artificially shift our clocks 1 whole hour for daylight time. And so we're already off of something close to the sun passing around the time the clocks say 12. But there's another factor that's quite important as well. And that is where you are on the Earth depends, of course, or determines when the sun is actually going to cross your north-south meridian line. And we have time zones that we use to keep our clock straight. So everybody in the Pacific time zone, which is, of course, hundreds of miles wide, uses the same time. But the sun doesn't cross the local meridian for each person at the same time. It has a different time for each and every person. In fact, everybody that's here today, it's a very democratic Griffith Observatory. You all have your own local meridian. I'm just standing on mine right now. But we still do keep the same clock time. So that's factor number 2 that makes the times not coincide with 12. The third has to do with the Earth's orbit. The Earth's orbit is not a circle. It's an ellipse. That is a kind of an oval circle. And that means there are times when we're closer to the sun and times when we're farther from the sun. And when we're closer to the sun, and that actually happens in wintertime, it's a small difference compared to the orbit of the Earth, but it's enough, in fact, to be measured. And we travel a little bit faster when we're closer to the sun than in summer when we're farther from the sun. And that faster travel accelerates the apparent motion of the sun across the sky. And so that, too, introduces a change in the way our clocks work. So we've at least dealt with the problem of why local noon isn't happening at 12 noon on the clocks. It's going to happen at 12:55. But how it happens is something else entirely. Well, you need a couple of things to do this. One of them is the local meridian. We've already got that north-south line that extends from the south here and goes to the north all the way at the far end of the transit corridor to the stairs, and up the stairs, that angle pointing to the north pole of the sky. This is all taking place, of course, because the sky is apparently rotating around us. Really, it's the Earth turning, and it's turning around that spot in the sky that you can see, at least locate, with the star Polaris if you're here at night and look along the banister. So that gets us started with this Gottlieb Transit Corridor instrument, but there's more to it than that. To the south, there is the large black monolith, and the black monolith is there to support the stainless steel foil, and the stainless steel foil is there to provide the most complicated aspect of the Gottlieb Transit Corridor. The most complicated aspect of the Gottlieb Transit Corridor is the hole in the stainless steel foil. So celestial objects pass across the sky, their light passes through the hole, and in fact the sun's light not only passes through the hole at local noon every day, it's passing through the hole right now. And we are just picking up the first little bit of the spot of sunlight that is coming through the hole in the foil onto the meridian arc. Now, the meridian arc is intended to keep track of how the sun migrates up and down at local noon through the course of the year. Today at summer solstice, the sun is at its highest point we ever see it in the sky from here in Los Angeles. It's almost overhead, and so the spot of light is coming almost straight down here. It's coming on the line that's marking the constellation Gemini. It's marking the line that's the 21st, and here, in fact, is the marker for the summer solstice position. But over the course of the year, if you watch this continue, this would actually climb up higher and higher up to the arc to the point up at the highest for the December or winter solstice and back down again. So we've got marked on here the months, May, June, July, August, and so on. We have the dates for June, for example, the 1st, the 10th, the 20th, and so on. And we have the zodiac constellations through which the sun appears to move through the course of the entire year. Already, the spot of sunlight is on the meridian arc and headed for the center line. So when it reaches that center line, it will, in fact, be local noon. But this you would say is not very imaginative. What have we done here? Well, we've taken some Stone Age astronomy, we've taken some Bronze Age construction, and then we've taken a little Renaissance ornamentation and put them all together. And you say, is that enough for a 21st century public observatory? And of course, the answer is no, it's not enough. So what you have to see as well is the ecliptic chart that maps out the path of the sun through the course of the year and passes through those zodiac constellations. And if the transit corridor operates correctly, when this sunlight crosses into the center line, it will activate by sensors the position of the sun in the constellation Gemini, which is up there now, but you can't see it because it's daytime, and the stars of Gemini. So local noon on the ecliptic chart has just been marked, and the spot of sunlight continues to move across. Ladies and gentlemen who are here in the audience, it is time for you to applaud local noon at Griffith Observatory. Now we have one more step to undertake. And this is a puzzle. This is a riddle for you. If the sun is down here at summer solstice and it goes up to there at winter solstice, but then it comes back down here to summer solstice, it goes up and down in a year. The sun also moves through that entire arc of line through the zodiac constellations in a year. And the instrument is telling which constellation to light up. How can the transit arc possibly know whether the spot is going up or coming down? Is it this side or this side? How can it know how to do that? Well, the answer is the switch. We have the big switch, which we turn at the solstice so it operates at the right time of year. Now, very quickly, I need to know who's here from the farthest location from Los Angeles. India's pretty far. Can anybody beat India? That's halfway around the earth. Please come down, sir. We've still got local noon marking on the Meridian arc and the sun's position still in the constellation of Gemini, the twins. You know, for coming from India, you made the trip pretty fast. Thank you. Where in India?
I come from Delhi.
From Delhi, of course. Please come over. And this is the switch. So all you have to do, we need a large round of applause for this. Please lift this up and turn it all the way over. Thank you, sir. And you are all in his debt. Tell us your name, please.
Mansoor Ahmed. Mansoor Ahmed.
So, Mansoor Ahmed, we are grateful. We're actually going to work for another year, or at least half a year. And so for that effort, first you get a Welcome Back to Griffith Observatory button. Is this your first time here?
Oh, first time.
Well, then that button means you get to come back. And then here is your Signs of Life Griffith Observatory Planetarium Show button.
Thank you so much.
Thank you for being here at Griffith Observatory. Okay. So, ladies and gentlemen, that closes local noon at Griffith Observatory. It is the summer solstice, and the bad news is just as we're finally getting some sunshine, the days are going to get shorter. See ya at the next event, autumnal equinox in September.
Well, thank you, folks, for joining us today for the Northern Hemisphere Summer Solstice, our solstice presentation live from Griffith Observatory here in Los Angeles. Once again, Griffith Observatory is owned and operated by the Department of Recreation and Parks in the city of Los Angeles. And as always, we thank Griffith Observatory Foundation, our exclusive nonprofit partner, and everyone that makes all these wonderful events possible, and all of you that join us for them. Thank you so much for being here. And join us again tonight at 7:45 for our Sunset Solstice show. Thanks, everybody. Have a great afternoon, and we'll see you this evening.